A curve drawn on a page suggests a measurable area, but 19th century analysts required a formal method to calculate the space trapped by a line containing infinitely many points. This chapter provides the rigorous foundation for that measurement. While it is easy to estimate area by looking at a sketch, proving it exists mathematically requires us to abandon the drawing. We must build a logical bridge between geometry and pure algebra. Definition 6.1 introduces the partition. We take the interval on the x-axis beneath our curve and divide it into a finite sequence of points, x sub 0 to x sub n. The distance between any two adjacent points is the width of a single segment, defined as delta x sub I. Inside any single segment, we identify two values, the absolute lowest point the function reaches, m sub I, and the absolute highest point, m sub I. Establishing these definitive high and low ceiling values for every segment is the mandatory first step. It creates a rigid mathematical cage that will eventually force the true area to reveal itself. We use the lowest points to calculate our lower sum. By drawing rectangles up to mi for each segment, we build a shape entirely beneath the curve. Because of the empty gaps left over, this area is a guaranteed underestimate. Conversely, calculating the upper sum means drawing rectangles up to the highest points, mi. These rectangles break through the curve, resulting in a guaranteed overestimate. In equation 1, we identify the tightest possible underestimate by taking the supremum, the highest value, out of every possible lower sum. Then, in equation 2, we find the tightest overestimate by taking the infimum, the lowest value, out of all possible upper sums. We now have a best-case lower boundary and a best-case upper boundary. If those two values perfectly match, the function is officially Riemann integrable. The gaps disappear, and the area is a proven mathematical fact. Definition 6.2 generalizes the integral by replacing the standard physical width of our segments, delta xi, with a monotonically increasing weight function, alpha. Geometrically, alpha acts as a weighting factor. While the standard integral treats every inch of the x-axis equally, the Stieltjes version assigns custom weights, changing how wide a given interval behaves mathematically based on its location. This removes the constraint of strictly measuring geometric distance, allowing us to calculate values for uneven mass distributions or varying probability densities. Returning to our approximations, theorem 6.4 explains how to improve them using a refinement. A refinement, P star, is created by taking an existing partition and adding a new point, X star. Adding that point splits one wide rectangle into two narrower ones. Since the highest point in these new, smaller intervals is lower or equal to the original, the rectangles drop down, hugging the curve tighter and eliminating wasted space. Now, visualize exactly what happens to the area of the underestimating lower rectangles when we add that same point. The lower rectangles rise to capture more area. As overestimates drop and underestimates rise, the gap shrinks. This leads to theorem 6.6. A function is integrable if the difference between upper and lower sums is less than any arbitrarily small number, epsilon. Theorem 6.9 and 6.10 confirm that continuous functions and monotonic functions both pass this squeeze test. Theorem 6.6 is the analytical gatekeeper. It proves that if the error between the upper and lower sums can be forced toward zero, the true area is permanently trapped. With integrability established, theorem 6.12 defines the mechanical properties of the integral. These equations confirm that integrals are linear. They can be added together or scaled by a constant while maintaining their properties. Scaling a function's formula mathematically scales its physical area by that exact same proportion. The logic of the chapter resolves into a precise sequence. First, upper and lower sums create the initial bounds. Second, partition refinements tighten the approximation. Finally, the epsilon squeeze proves that as the gap shrinks to zero, the integral is defined. This level of rigor is what allows us to derive the fundamental theorem of calculus later, ensuring we can apply calculus to physics and statistics without encountering logical paradoxes. By replacing visual intuition with formal proof, we establish the logical certainty required for the higher-level analysis that follows. If you want to continue exploring the mechanics of analysis, subscribe for more.